Hello, everyone. My name is John Stancarone with T Equipment. I'm an engineer and product specialist. Thank you very much for joining us today for the webinar. Megger presents Transformer Testing. This is going to be a really great webinar. We have Yash Kadwani, application engineer, and Ken Petroff, business product portfolio manager with Megger, and they will be presenting the topic Transformer Testing. Yash holds a bachelor's degree and a master's degree in electrical engineering. He's been working with Megger since March of 2020. Yash has a very good experience working with transformer testing as well as testing other assets in substations. He also specializes in cable testing, including but not limited to partial discharge, TAN Delta, VLF, etc. He's an active member of IEEE and CIGRE. Ken has direct responsibility for the transformer product category of portable offline transformer test equipment, and he began his career at Megger 11 years ago in the engineering department as a software technician and design assurance supervisor before moving into product management in 2018. He uses his organizational communications degree to bring a unique perspective to the design of test equipment, focusing on the undeserved customer needs of user experience, training, results interpretation, and asset assessment to improve customers' maintenance activity decisions. So before turning over the presentation to Yash, who will begin, and we're going to wait for a couple of late joiners to start as well. I've got a couple of slides to show you about ourselves. I wanted to tell you a little bit about T Equipment. We've just recently celebrated over 21 years in business. We're heading on to 22 years now. And in that time, we've become a very large stocking distributor. We really do take to heart the slogan, buy from people, not just the internet, and we have a qualified staff here to help you. As you can see from this slide, as a national and international distributor, we do cover the needs of a wide variety of customer types on the left-hand side. You can also see the types of equipment that we carry on the right-hand side. In total, we carry more than 500,000 products. Now, our company has invested very heavily in making the website a great resource. You can see the filtering capabilities that we've introduced by specifications, price, many other different factors, including voltage, things like that. On the left side of the page, that's on the margin there in the gray. You can see that we also have ability to ask for a quote, to ask questions, things like that. We have feedback where we get back to you right away. You can see that we do constantly update this. So it's updated regularly with new products and with new features and refinements. So we're always working on it, definitely proud of it. And I think it's going to be very useful for you to be able to use to find the products you need. Now, without further ado, I'm going to pass the baton on to Yash, and he's going to start his part of the presentation.
All right, I think everybody can see my screen, so I'm just gonna go ahead and start. So I'm gonna cover the first part of the presentation, beginning theory over a little bit of insulation resistance on transformers, winding resistance, and ground testing on transformers. I'll also share what kind of equipments you can use and how to do the testing, why do we do such testing, and what's the theory behind it. So let's begin on our agenda today. We have diagnostic testing of insulation, a little bit of theory part and how it works. Then MIT, that's one of our insulation tester. And then we will cover a little bit about winding resistance, theory and application, as well as earth testing on transformers, the digital earth tester, theory and application. And then I'll pass over the baton to my colleague Ken, and then he'll cover a little bit about turns ratio testing on transformers. So insulation resistance, why do we do these tests? The main function is to check the integrity of the insulation, whether when you supply the voltage, is it able to hold the voltage without losing or leaking to ground, avoid arcing at different voltages or leaking to earth, obviously protect the personnel to avoid any electrocution or shocks to the personnel, And as an alternative to keeping a distance, you have insulation to protect any personnel that is there. What are the fundamentals behind IR testing or insulation resistance testing? I'm going to use IR a lot. So that's what I mean when I'm saying IR. It's just insulation resistance. So don't get confused or lost there. So insulation resistance is basically you're using a DC current in order to measure your resistance. It's basic principle of Ohm's law. You are keeping your voltage constant and you are measuring the leakage current, which gives you in terms of equation your resistance. And the main purpose is to measure the resistance and not destroy the insulation and identify aging if possible. If you're trending results, that's when you can see how the insulation is aging or degrading over time. It is not a withstand test, so keep that in mind that it's not you just rank it up all the way and you just do a withstand test that is for so and so time does it hold the voltage. No, IR is a little bit different than that. It is just to measure the resistance. Insulation does not prevent the current flow. It has a finite resistance, so always make sure that you are using a voltage that is appropriate for the type of equipment that you are doing it for. Let's say your motor or generator is only rated for 1000 volts. Don't do an insulation test of 2 kV or 2.5 kV. And insulation can be considered as a capacitor in parallel with the resistor. So what is a capacitor? Basically, it's two conductors separated by an insulation. So that's your basic capacitor. And insulation can be considered as a capacitor in parallel with the resistor. So the theory behind insulation resistance is that you have three different current components playing there. You have your capacitive current, you have your absorption current, and you have your leakage current. So whatever all these three different components you'll see when I talk about a little bit further, I'll also show you a graph of how these different currents play into picture. Uh, Firstly, your capacitive current is only flowing for a short time until your object under test is charged. So that's your first component of the picture. That's your capacitive current. Second is your absorption current. That is the amount of current that is used to align all the dipoles in the same direction. As you see in the diagram right here, turn on my laser pointer. Right here, you see that all the dipoles are aligned in a single direction. So the amount of current that is used to do that is your absorption current. And lastly, you have your leakage current. So that is whatever is leaking to ground or any other object nearby, that is your leakage current. This is the graph that I was talking about. Usually within the first few seconds, this is your capacitive charging current that dies down within the first few seconds. It is just used to charge the object under test. Second one is your absorption current that lasts a little while longer, about a minute or so. And then you have your leakage current that is that increases with time and stabilizes after about 10 minutes. It usually stabilizes much faster, but at 10 minutes, what you see is definitely everything leakage current. And these readings that you get, whatever gigaohm or megaohm or any reading that you get, are time and temperature dependent. So time, we already discussed what combination do you see in which part of time. Also, temperature plays a big role. Whenever you are measuring any type of resistance, it is always temperature dependent. So we need to account for that factor that it is playing into picture, and that's why most of the times we correct it to 20 degrees C or 25 degrees C depending on where you are, and that gives you comparable results. So that because one day you're going to test at 15 and the other day it might be 25 or 27. So you need some comparison between the two, and we use correction factors and everything like that to correct it to a specific temperature to make the results more comparable. So what is the basic insulation tests? When do we do it and why do we do it? Basic insulation test, you apply a voltage, terminal to ground, or terminal to terminal, depending on what is your aim behind the performing the insulation test, and measure the resistive current or leakage current. Normally, you apply the test voltage for at least 1 minute to allow the capacitive and absorption component to die out, and whatever then you get is mostly your leakage current, and that's what you want to measure, and based on that it will throw out a resistance reading. So that's why it's important to wait a minute before actually taking the reading. And it should be non-destructive. Of course, you are not there to destruct your insulation, you are just there to test it, what is the integrity of the insulation. And at the very end, very important, discharge the test piece, basically ground it once you are done doing the testing. Some some insulators are slightly different than the others. For example, oil would have slow breakdown, slowly increase until breakdown occurs over a fixed gap. The voltage would be measured. If you have seen a oil 10 delta test or oil breakdown voltage test, you are basically filling up filling up a vessel with oil, and then you have your two electrodes separated by a gap of 1 mm, 2 mm, 3 mm, depending on what kind of oil test you are doing. And then whenever there's a flashover or breakdown happens, you slowly, gradually increasing the voltage, and that's when breakdown happens, and then it drops down. So that insulator is slightly different than the other, your normal insulation test. What's your purpose? Meet the minimum standard without breaking down. So definitely that's your main goal, that it holds the voltage without leaking to anything else. Ensure there is no transit damage, specifically when transformers are transported to different locations sent out by the manufacturers. A lot of times what happens is they are either damaged during transport or while they were loading and unloading stuff. There's a lot of chances that it might get damaged during the transit. So definitely you're checking for that aspect. Environmental factors that have not damaged the insulation. So those also play a big role. Uh, when you are commissioning a transformer, you want to make sure that there's no environmental factors that played a big role. There's no moisture or dirt sitting on the bushings or contacts or whatever. And monitor the quality of insulation over a lifetime. You also want to set a baseline when you initially commission a transformer. You would take your Megger readings and put them down on a form or write somewhere so that you have a baseline to compare to in your future. So that's what your main goal is. What to test and what voltages. Typical equipment that may be tested can be transformers, motors, switchgear, circuit breakers, switchboards or motor control centers, MCCs, disconnect switches, insulators, bushings, cables. Pretty much everything that is in a substation can be done an insulation resistance test on. And this is what I was talking about, typical test voltages. Equipment up to 1000 volts, test at 500 volts. Equipment at 1000 to 3300 volts, test at 500 to 1000 volts, so on and so forth. Uh, Motors have a little bit different IEEE standards compared to everything else. So those are as listed here as well. So they have a little bit different limits, if you will notice, than your typical other equipment. So those are your typical test voltages that you would test at for different rating of equipment. Now, important part, how to connect. A lot of it is simple, yet a lot of chances that it might be messed up or there's a chance of error there. Firstly, you have your test leads. You have a positive and a negative. Usually negative is the one that is going to the conductor, and positive is the one that you're hooking up to the insulation or ground, whatever you're testing at. it is normal to connect positive connection to ground. So that's what you are doing in this case. And positive is the one that is measuring for leakage current. In the analog style equipments, that's what it used to be. But in the digital ones, it doesn't matter much if you do it the other way around as well. But just make sure that whatever is under test, everything else is hooked up to the positive terminal or negative terminal, depending on how you are connecting it. And everything else is grounded other than the object under test. Most of the times, there's a third terminal, which is the blue one, that is the guard terminal. A lot of people don't know the use of the guard terminal, and I will cover that a little bit further in my presentation of what exactly is it used for. Usually it's a blue lead that you get with your Megger test set, and most of the time people don't know what that is for, or it's just there and never used it kind of thing. I will cover when you need to use that. So there are different types of insulation resistance tests that you can do on an equipment. There is a short time spot reading that is basically you connect your equipment, measure, and boom, done. So you are doing a spot reading, that is you're essentially connecting the instrument and immediately taking a reading after your test voltage is reached. That's your spot reading. Then you have your time resistance method. That is, you are supplying the voltage for X amount of time. That X amount can be decided by the user. It's 30 seconds, 60 seconds, 1 minute, 2 minute, whatever. So that is time resistance test. You're basically defining that I want to test it for X amount of time. Then you have your DAR, or dielectric absorption ratio. That is your ratio of 60 seconds to your 30-second reading. So the instrument takes one reading at 30 seconds, the another one at 60 seconds, and it gives you a ratio about that. Polarization index, this you will see a lot in transformers. We always do a PI test on the transformers. So it's your 10-minute reading to your 1-minute reading, similar to a DAR, but just time is different, 10 minute to 1 minute rather than 30 seconds to 60 seconds. Step voltage is basically if you have to say, I want to do a test at 5 kV, you just don't increase all the way up to 5 kV. You go in steps, 1 kV, 2 kV, 3 kV, 4 kV, and then you reach 5 kV. So you are taking, at each step, you are taking an insulation reading, and that's your step voltage test. And your dielectric discharge, that is when you are discharging it, that's when you are accounting for a curve, how the object is discharged, and that tells you a little bit more information. So that is not very common, and a lot of people don't do it. It's more popular in Europe, but it's good to know. And these are all the different graphs that that you get from all the different kinds of tests. Your PI test, your DAR test, 60 seconds to 30 seconds ratio, and this one is a good insulation condition determination, that whatever it is, if your PI test result is less than 1, then you know that insulation condition is poor. 1 to 2 is questionable, and so on and so forth. Similar for a DAR result, anything that is less than 1, definitely it's a poor condition on the insulation. The reason being that your 1 minute is at the bottom and 10-minute is at the top. So if your 10-minute reading is lower than your 1-minute reading, obviously your insulation is degrading. Because with time, if you see on the previous screen, the insulation reading should go up as you go up in time. So this is time versus megohm, so it should go up and not down. If it's going down, that means it's a poor insulation. There's that. And now moving on to, let's actually test a single phase transformer. This is your basic test equipment. Negative is connected to the low side. Positive is connected to the high side. And now I'm using the guard terminal, that is a G, and hooking up to ground. The reason why I'm doing that is I want to ignore any leakage current that is going on the surface of the transformer, that is on the tank. Anything related to tank, I don't care about. I just want to see how the insulation resistance reading is between my high to low winding. So that's all I care about. I don't care about the surface discharge. So whenever I hook up this guard terminal, anything that this guard terminal reads is subtracted from your actual reading. So any leakage current that is going through your surface is going to actually be subtracted out from the reading, and that's how it will give you an insulation resistance reading. That's what the guard terminal is used for. Anything that you want to guard out of the measurement, you can use the guard terminal. That is the blue terminal. Similarly, if I want to do it the other way around, I want to measure between my high side and my ground, I would just hook up my negative to high side, positive to ground, and I don't care anything about the low side. So I'm just guarding it out of the measurement, and that's how you will know that you are specifically measuring only between high side and ground. Similarly, testing a cable. So you are hooking up your center conductor. I want to test white phase in this case. I'm hooking up my center conductor to the negative, and everything else I'm just hooking up to the positive, and I don't care about the surface discharge from here. So I'm just braiding a copper wire or any metallic conductor to the wire to the surface, and then I'm guarding it out so that any surface discharge I'm negating from the actual measurement. So that's how you test using a guard terminal. That's the actual use of guard terminal. Now, now we know how to test insulation resistance. We know theory about it. So let's jump a little bit to transformer ohm meter overview. That's basically your winding resistance. When do you do it? Why do you do it? What does it tell you? So why you can detect short circuited turns in the transformer itself, any anomalies due to loose connections in the transformer, you can detect that using winding resistance, broken strands, high contact resistance in tap changers. So it's all integrated in the winding resistance test, and from those readings, you can determine any kind of insulation defects in the winding. When do you do it? It's usually installation commissioning test, internal transformer inspections, factory test, heat run, any kind of routine maintenance or unscheduled maintenance, or you're troubleshooting a transformer, that's when you do this kind of test. It's one of the most common tests that you see in the field, TTR and winding resistance. Those are two kind of bread and butter tests for a transformer to perform routine maintenance. What is the principle behind transformer winding resistance measurement? Firstly, we are using DC current in order to measure resistance on the transformer. Now, why do we use DC? Why not use AC? Because transformer is an AC equipment, right? Why does it make sense to use DC? The reason being, your winding is made up of some resistive component and your inductance component. Basically, winding is wound around a core, and that's what generates inductive component in the winding. So I don't want to care about the LDI by dt. That's your basically inductor part of it. I don't want that. So what I do is I just care about my resistive components. So I want to negate this part. So what I do is use DC. DC only measures for resistance. It does not measure inductance or capacitance. So that's why I'm using DC in a transformer in order to account for only resistance measurement in a winding. These are the typical leads that come with your instrument for three-phase. You have your three phases and a neutral in some cases. So definitely your Y winding when you need one. Principle of measurement, the change in current needs to be zero. This is important. A lot of people just take winding resistance measurement spot on, and there you go. It's not like that because your resistance keeps jumping around until your current is stabilized. How do you attain current stabilization? By saturating the core of the transformer. The larger the winding, the greater the difficulty. That means it's harder to saturate a bigger transformer rather than a smaller transformer. So that's when your current and voltage play in place a lot, because the more current that you supply at a higher voltage, your core saturation will be faster. So that's what it's saying here. Two important aspects: your open circuit voltage or your compliance voltage and applied DC current. Two important aspects to keep in mind while doing a winding resistance test. Voltage helps in saturating the transformer core, and higher current provides early stabilization. So you are not waiting there for 2, 3, 4, 5 minutes for the current to stabilize, and then you get your reading. So how much current and voltage is sufficient to obtain fast and stable readings? It actually depends on the rating of your transformer itself. You have your line-to-line voltage. In this case, it's 68.8 kV to 13.09 kV. And based on the MVA rating, I have my rated current primary and rated current secondary in this case. And that's why I'm using 10 amps current on both the sides. What is the typical requirement, or what is the recommended current and voltage? I'll go through that in the next slide, but this is just showing you what compliance voltage, how much faster the reading is. So for 6740 volts, X1 XO, you get a stable reading in 37 seconds because it's 67 volts. And at 40 volts, you get the same reading at around 1 minute and 7 seconds. So you see the time difference there because of higher voltage. So that's what it's explaining you, that based on your voltage or current of the transformer, select an appropriate current to stabilize. Now, how much current should I select, right? Based on your rated winding current is typically determined by your MVA and kV rating on the transformer. So whatever your rated winding current is, select 0.1% to 15%. Never exceed 15%. Anything between 0.1 to 15, and recommended to inject 1%. So if my rated current is 100 amps, I would just inject 1 amp in that case. Now, if the test current is too low, then the measured resistance is not consistent, depending on the magnetic status before the test started, of course. And we are never to exceed 15% of rated winding current. The reason being, when you do that, there can be residual magnetism in the transformer core that can leave it magnetized. And when you inject AC, it can create some disbalance in the transformer, or it can create heating in the winding and keep changing the resistance. So that's why it's advised never to exceed 15% of rated current. Now, current should not be, these are all the safety considerations, so very important. Current should not be interrupted abruptly when the test is finished. You need to leave the current discharged. And the safest way to do it is bring the current down slowly to zero, and after completion of the test, and discharge the test object by dissipating everything to ground using limiting resistors. This is all done internal to the instrument itself, but it is just necessary to know what's happening behind the scenes when you complete the test. And ground circuit should always be in place to absorb the stored energy using limiting resistors. So always make sure you have a good grounding connections. Once the test is done, it is all going to ground. And the instrument itself will give you a safety indication that whenever it's safe, it has discharged all the energy that it supplied to the winding. It's going to discharge, and then it's going to give you, okay, now it's safe to disconnect the leads. So that's when you disconnect the leads. And what is the pass or fail criteria depending on my winding resistance measurements? How do I know what is good, what is bad, right? The resistance between phases should be within 2% of each other. This is determined by IEEE standard C57.152. This standard says that each of your phases should be within 2% of each other. And comparison can also be made to the original data measured in the factory. So whenever you get a transformer from the factory, you get some test reports. What were the tests that were conducted when it originally left the factory? So you can also compare it to that data. Agreement to within 5% of any of the above comparisons is usually considered satisfactory. So if you're comparing to the original data or even any other comparisons, within 5% is what you're looking for, and that's your pass or fail criteria basically. Now, how is the testing actually performed? What goes on behind the scenes? This is a typical example of single phase testing on the transformers. You have your current source and you are trying to set up flux in an appropriate direction. So how does your current flow? Your current source is hooked up here. So your current is flowing in this direction and then circulating through this winding and coming back up to XO. So X1 to XO. Now it's important to understand how the flux is set up in the transformer. The reason being, if you supply the flux opposite to whatever it was set to, it will take much more time than what is required uh, to set up or to stabilize the current in that case. For example, if you are doing A phase testing, your current is flowing from H1 to HO and your flux is getting set up in this direction, right? And you want to make sure that you are testing adjacent phase to set up the flux in the same direction. Otherwise, you're working against the flux. So you have to give it more time in order for it to stabilize. So when you are moving on to the B phase, you are supplying from HO to H2 to make sure that the current is in upward position and your flux is getting set up in this direction. So it was getting set up in the same direction in the previous test, if you notice here, and that's why you are moving in the same direction of the flux, which helps you in getting a faster reading rather than saturating the core in the opposite direction. And similar to phase C, your phase flux is going H3 to HO. So you are going from H3 to HO, your current is in the downward direction and flux is in the upward direction. So it's aligning with all the three. If you notice, it's aligning with all the three different phases. And that's how you are making sure that you are moving in the direction of the flux and not working opposite to it. That'll help you achieve the winding resistance measurement much faster than anything else. And that was for Y winding. This is for delta winding. Similar concept, just move in the direction of flux, not opposite to it. It will help you attain the saturation much faster. Now, whenever we perform a winding resistance test, which is a DC test, what is necessary after performing it? Demagnetization, right? Because your transformer is an AC component and you don't want to leave any residual magnetism inside it. Because what can happen if you have residual magnetism, it can, once you connect it back to AC, it will have a higher than normal excitation current, as well as there could be sparking at the contacts while initially connecting it, and it can uh, prove to be a hazardous situation in that case. So definitely, as per IEEE C57.152, demag is necessary after performing a DC test or winding resistance test in that case. How do you do a demag test? Basically, you are applying whatever it is, it was 100% of test current in positive magnitude, and then you are doing a negative 100%, positive 20, negative 20. So you're basically decreasing your magnitude over time, whatever it was injected for. So you're doing positive, negative of DC, and that's how you're reducing the residual magnetism in your transform. So you're basically removing all the flux that you set up. This is this might remind you of your university or school days. This was a BH curve that everyone studied in their university education. This is how it's actually going up, and it's gonna move the residual magnetism positive, negative, and then it's gonna move up back to uh, 0 in that case. This is the current magnitudes that are being applied by the test equipment: negative 10, positive 6, minus 3.5, 2, minus 1. So these are different voltages, currents that are being applied. And if you notice, those are only being applied between H2 and H1. The reason behind that is usually your transformer is sorry, your transformer is a three-legged component, so it's something like that. And you have your middle leg right here, and this is your H2 H1. In that case, your H2 and H1 winding would be on your middle leg, and this is where you demag from. So it is easier to remove the flux in both directions from the middle leg rather than working on each side. So that's why you always do it on the middle leg to easily remove the flux from both directions. And what are the other complementary tests that you can do on the transformer? You can do turns ratio, excitation current, leakage reactance, sweep frequency response, that is SFRA, or power factor. Now, let's move on to the earth ground testing, a little bit about the transformer itself. What is a ground? It basically provides a low resistance path for anything to dissipate or discharge, typically fault currents, lightning strikes, any static charges in the equipment, or any residual EMF. Types of grounding systems: you can either have single rod or multiple rod grounds, depending on what kind of system you have. It can be so many types of ground. You can have multiple rod ground, buried plate, or buried mesh inside the grounding system itself. So there's so many different arrangements that you can have in depending on where you are, right? What is the benefits of proper grounding? It reduces the chances of injury to the personnel. Any kind of lightning strikes can immediately be grounded. Uh, any electrical noise that is unwanted can be grounded as well. And it protects against static electricity from friction. Let's say you have a motor that has a belt, and it can build up static friction or static electricity over a period of time, so that can be grounded as well through a good grounding system. And it limits the definite values of voltage to earth of the entire electrical system. So it's a very key component when you have a good grounding. And why is it important to test? Because obviously grounding system is not eternal. It degrades over time. It causes there's usually metallic corrosion or any kind of external mechanical strain that is laid upon the grounding rods or plates. So you have all those different factors playing into picture, plus any kind of catastrophic events like lightning, storm, large fault currents can cause an instant degradation of your grounding scheme. So it's very important to test those. Um, Usually, when a lightning strike occurs, your grounding system is good. It survived that lightning charge, but it also kind of took a lot of strain on the grounding system itself. So next time it might not be as accurate, and after 2, 3 instances like that, the grounding system might even fail, and that's when you would have a potential risk of failure of the whole system. And what is the difference between ground resistance and earth resistance? A lot of people confuse this, that ground electrode resistance is the resistance of the electrode system itself. It is usually in ohms, and it should be low enough to dissipate all kinds of fault currents, lightning strikes, etc. Whereas earth resistance or earth resistivity is the electrical property of the soil itself for conducting current, and it is measured in ohm centimeter, and this is measured in ohms. So anything that you see in ohm centimeter is the resistivity of the soil itself, and anything that you see in ohms is the ground electrode resistance. So something to keep in mind when you're looking at readings. This is a key difference or key indication that you have one or the other. What are the typical good values for a good ground system? Some call 5 ohm maximum, that is in nothing more than 5 ohms for a grounding rod, or a fraction of an ohm. Fraction of an ohm is anything less than 1 ohm is considered to be good. Typical values from an insurance company point of view: for industrial plant, nothing more than 5 ohms, chemical plant 3, and computer system 3. And typical values for a power company or utilities, nothing less than 1 ohm for generating in large substation, small maybe permissible to up to 5 ohms. So these are your typical good ground values. A lot of time we get asked in the field that what do I consider good and bad? So this is a good reference to keep in mind. Now you have different kinds of different kinds of earth testers in the market. You usually have 3-terminal testers, 4-terminal testers. When do you know which one to use? It depends on what you are looking for actually. 3-terminal has a little bit less accuracy, but it is comparatively easier to use, labor intensive wise, whereas 4-terminal is highly accurate, but it is more labor intensive. Now, how do these methods work? It is typically a fall of potential method that most of the guys use in the field. You have your 61.8% rule or 62% rule method, that you are placing your potential probe at 62%, somewhere around here. And that's when you will have a constant or true reading that is stable and without effect of any earth shells of the grounding system itself. And that will give you a true resistance reading of the grounding rod. And you have your 4-pole potential method that has several different methods in intersecting curves, slope, dead earth, and star delta. We don't have actually enough time to explain all of that, but these are some of the different methods inside 4-pole testing. Advantages of fall of potential method, and the 62% one, is it's extremely reliable. Disadvantage, extremely time consuming and labor intensive. So it's also, when you are measuring 3-pole, you have to measure for 62%, go to there, dig up the ground rod in there and measure it that way, and you have to do it at several different points. So what's the alternative? You can use simplified fall of potential. Basically, you make 3 different measurements at 40, 50, and 60%, and then you take an average of those measurements, and you can use that as your grounding rod measurement. Advantage in being much faster and simpler than a full fall of potential method, but it is less reliable since fewer measurements are being made. So it's less accurate, but it serves the purpose rather than doing a full fall of potential method. So my part of the presentation is over. I'll hand it over to Kenneth Petrov to cover our TTR part of the presentation.
Yeah, thank you very much, Yash, for your presentations there. Let me go ahead and get my presentation queued up here. I am ready to go whenever I get the control here. Share my webcam, no. Did you pass it back to John, Yash, or did you pass it over to me?
I just passed it over to John.
Okay.
Thank you very much. So let me see if you have it now. I have, looks like Jessica, I've got you as a presenter. So let me know if one of those is you, Ken, one of those names, or I can change it.
Oh,
There we
yeah,
go.
I was sent to a panelist. Yeah, so I guess I clicked on the wrong link there. I think it's the other one that needs to be the presenter, the other Jessica
Okay.
East.
Oh,
Sorry
great.
about that, John.
No problem at all. I just made it, see if that you have control now. Yep, you should have it now. I have it under Jessica East, organizer, presenter.
I think, I'm sorry, John, I think it has to be the other one.
Oh, okay, no problem. I can change that as well.
Yeah, the one that says panelist.
Here we go. How's that?
There we go. Ah, that's much better. So you should be seeing my screen now.
Yes, I see your screen. Thank you very much.
All right, yes, thank you. Hola desde Chile. Thank you, everyone. I am coming in from Chile in South America. So first off, apologize if there's any delay in what you're hearing or seeing. I've shared my presentation with Yash and Jessica just in case I get bounced off here. But thank you, everyone, for being here today. Thank you, TE Equipment, for organizing this, and Yash for your presentations before. My name is Ken Petrov. I am the Power Transformer Product Manager based out of Valley Forge, Pennsylvania, and I'm here today to introduce the TTRU-1, Megger's latest handheld turns ratiometer that was launched in October of last year. I do have the agenda here today, and what we will be going through is first an introduction to the TTRU-1 product. Then we're going to discuss, why are we doing turns ratio testing? As Yash said in his presentations, complementary to winding resistance or insulation resistance, turns ratio is one of the first tests that we run on a transformer. Then we'll be looking at some go, no go testing of smaller distribution transformers where we're looking for short circuits, open circuits, and making sure that the core is there doing its job. Last, we'll take a look at the user interface, and then we'll circle back to the summary at the very end. So a first look at the TTRU-1. This is a true handheld turns ratiometer. It comes in a little backpack bag, not really a backpack, more of a belt loop bag. So that way, if you're going up in a bucket truck or you're in some tight locations, you can have it on your person. And then that keeps your hands free to use the leads and then connect them to the top of the instrument and connect them to the transformer, and then perform your tests without having to set the instrument down. The TTRU-1, as its name implies, is a single phase source and measurement turns ratiometer that has up to 62.5 volts induced, plenty enough voltage for any size distribution transformer you may be testing, up to 1 or 5 MVA. With an accuracy of 0.05%. And the accuracy that's required when you're doing turns ratio testing is 0.5. So when you get results with the TTRU-1, you can be confident that you can trust them in whether they tell you the transformer is failing or it's passing. We then have that go, no go transformer testing that I mentioned previously, where we look for open circuits and short circuits within the transformer. And when we talk about the transformers, I said 1 or 5 MVA, and that includes single phase and 3-phase transformers, as well as instrument transformers like current transformers and potential transformers. And lastly, the accuracy of the instrument is guaranteed across all of the climate extremes that you may be working in, whether you're in Arizona in the summer or you're in Montana in the winter time. The TTRU1 will be reliable and give you the results to make better informed decisions about your assets. Looking at a few of the features of the TTRU1, the first is the full color high bright display. As with most instruments that come out today, we are moving away from the old yellow backlit displays to something that can be more informative. And the way we use that in the TTRU display, the vector group of the transformer that you're going to test directly on screen along with the connections. In the past, you may have required a sort of cheat sheet that told you how to connect to certain transformers, but now we've incorporated that into the instrument itself. In addition, in the advanced model, we have the ability to save custom vector group. So that way, if you have the same, say, 5 or 10 transformers that you test routinely in your system or through your service company, you can pre-configure the device with those vector groups and eliminate all the other ones that you don't use. So it makes the test setup, execution, and results interpretation very simple. It is a battery powered device, and AA batteries are nothing new, but what is new is the ability to charge the batteries using a USB-C cable. The USB-C cable is the same cable that you're using on your smartphones today, whether it is Samsung or Apple, because as most of us know, Apple is going to the standard USB-C type of cable. Thank you to the European Union. And with a full battery charge, you can test up to 1,000 turns ratio tests. So, whether you are in a parking lot testing a bunch of transformers or you're testing a few transformers a day, the TTRU1 will have the battery longevity to get you through that day's worth of testing. One thing that we include now in all of the models is the ability to enter the nameplate voltages of the transformer and then provide the pass-fail ratio evaluation directly on screen. And when you run tests, they are automatically saved. And we also have included on the top, as you'll see there, a USB, another USB connection, USB-A, and this will be used for a USB drive or for the optional 2-inch printer for you to keep a record of those results after they're saved on the device. And then last, as with many new Megger products, you have the software available to download onto your personal computer or laptop, and you can use that in simulation mode. So you can use that to either get a feel for the product before you've made any decisions, or you can use it for training on the product. And you can also create those custom vectors that I mentioned before, and then you can deploy them out to other devices. So quite a few different functions there for the simulation mode software you can install on the PC. But now if we look at the turns ratio test, what this product is built to do, why are we testing turns ratio? And I'm showing a large transformer here, not quite exactly the same as a small distribution transformer, but there are some common elements inside, mainly being the windings, the core, and the tap changers. If you use a voltage regulator, it does have a tap changer inside. And with turns ratio, you can look for problems like shorted turns or the core moving around, or problems with those tap changer connections as it's going through the different positions. And turns ratio is typically referred to as a pass-fail test. If turns ratio fails, then the fundamental electromechanical parts inside the transformer likely have an issue, and any other testing that you would do would not be worthless, but would just further confirm that this transformer has significant problems. So that is why turns ratio is typically the first test that's done on a transformer before doing anything else, because you want to understand, is the core and the windings doing their job and being able to transform that voltage as is required. And it can also be used to ensure the ratio and polarity of instrument transformers like CTs and PTs. When we talk about turns ratio testing, it's a very simple test to perform and to understand. And the way that it is performed is that we apply AC voltage that's greater than or equal to the line frequency to the primary winding. We then measure the voltage that's induced on the secondary winding. In this fashion, typically the voltage is reduced on the secondary winding, or stepped down as we refer to it. But then what you will do is you will just compare the voltages that you injected and the voltages that you measured, and that is your turns ratio. And then along with the nameplate, if you were to enter that into the device, it would give the percent error to that 0.5% limit that I discussed earlier. So fundamentally, one of the easiest tests to understand when it comes to turns ratio testing, not quite as involved as winding resistance you heard with Yash before. Well, with this device, we saw the opportunity to add in a different test mode, and there are some other instruments on the market today that do this, but this is called the go, no go, where we're looking for short circuits, open circuits, and we're looking for the inductance of that core to be present. And again, trying to make sure that those fundamental electromechanical parts in the transformer are present and in good working order. And with the go, no go test, we can easily identify, if there's a short or an open in either the primary or the secondary winding. And again, when we look for inductance, we're looking for that transformer core. We want to make sure that it is present and transforming that voltage properly. And again, as I mentioned just a minute ago, when you perform this short and open test, it will look at both the primary and the secondary individually. So that way you can pinpoint issues. And when you combine this with the turns ratio test that I talked before, where you can see if the transformer is additive or subtractive, and then you get the excitation current, the amount of current that's drawn under that no load test of the turns ratio, this go, no go test will again allow you to pinpoint where issues exist, so that way you can have better informed maintenance activity decisions for your transformers. Now looking at the user interface of the TTRU1, it's a very simple device with a rotary knob for the different function selection. So as you go from left to right on the device, you start with your typical turns ratio test, your TTR. You will then have the go, no go test in the advanced model, and then some settings. So, your date and time configuration, the maximum voltage that you want to inject, things like that. And then finally, you have the information screen. And for the basic and the advanced model, this is how you are going to export those results. Looking at the turns ratio setup, this is an example of one of the common single phase transformer vectors that we see on the market. And this is why we put that vector group directly on the instrument itself. So that way you can hold the turns ratiometer right next to the nameplate and say, yes, I'm confident that I have the correct vector group selected for the testing that I need to do. And then immediately next to that will be the connections for performing the test. This particular vector group has two different connections for measuring turns ratio, one from X1 to X2 and one from X1 to X3, and it will tell you where to connect the leads when you perform each one of those tests. And then once you've connected, and if you've entered in some nameplate voltages for the transformer, after completing the test, it will show you the calculated ratio with the percent error. It can also be switched. Instead of showing the exact percent error, you can have it say pass or fail. So if that is how you are typically reporting that in your business or in your utility, you can certainly change the TTRU1 to display the information how you want it. And then very important with these single phase transformers is to note whether it's an additive or subtractive polarity. And we show that right along with the percent error and the excitation current that was drawn during the test. And then a quick look at the go, no go impedance. The main point to make here is that, again, we are going to show you the exact place where this failure happens. And on this particular test, on a single phase transformer we had in the factory, what I did was I put a short across the secondary, or across the primary. And we see here that it is reporting that the short circuit was on the H side. So again, go no go is a great way to pinpoint issues if you see your turn ratio results aren't as expected. So in summary, the TTRU1, the latest truly handheld turns ratiometer from Megger, is a single phase source and measurement instrument for single phase and three-phase distribution, power, and instrument transformers that measures, of course, turns ratio, that go no go test, or the pass fail test that we talk about. We then give the short circuit, open circuit, and inductance evaluation in the advanced model, and then with the accuracy guaranteed across the entire temperature range. And then with those AA batteries with the built-in USB-C charger, the instrument will always be prepared for the day at hand. And then lastly, really focusing on that user interface, making it easy for people who are new to the job or they've been doing turns ratio testing for a long time. They can easily pick it up along with the automatic result savings of the device that will give you reports when you export to Excel, or that optional 2-inch printer. I've seen people, tape those up inside cabinets at the end of testing, and really allows the user to have the confidence that they've, again, set up the test properly by comparing the nameplate vector directly to the vector that's on screen with the clear test setup with the connection labeled right there, and then the clear results evaluation. And that's the end of my presentation. I'll throw it back over to John now. Thank you.
Great, thank you very much. So I'm got a couple questions that have been provided, and I'm going to work on that for you right now, and you guys should be able to answer those. One moment, let's see. There we go. So you should be able to see my screen. Good. Yep, that's basically contact information for myself. If there are any questions that come up that we have not answered by the end of the webinar, sometimes I know after the end of a webinar, some questions will come up, and certainly, you forgot to ask them. Well, we definitely will respond and get back to you with questions to your answers to your questions. Right now, we do have a couple questions that have come through. The first one was, can you revisit how compliance voltages were determined, particularly for bidirectional transformers? Specifically on BESSs, and I think this all really relates. Does the TTR need to be performed in both directions?
So, talking about compliance voltage, I know Yash had discussed that as part of the winding resistance. So compliance voltage, when talking about winding resistance, is more about saturating the transformer core. And with less voltage, it will take longer to do that. So the higher the compliance voltage, the better. Typically winding resistance test sets will have anywhere between 40 and 100 volts DC. Anything more than that, you're really losing the benefit of having the higher voltage. You're not going to saturate the transformer any faster if you have 200 or 400 volts DC for that test. At least it'll be imperceptible on smaller distribution transformers. But for turns ratio testing, talking about the voltage that's required to do the test, all transformers are voltage dependent. So if I take my turns ratiometer and I tell it to inject 1 millivolt on the primary winding, it's not going to generate enough flux to transform that voltage to the secondary side. And what we see with most distribution transformers, especially pole mount, 8 volts has been plenty enough to get a good transformation of voltage. But with the new devices, as components get smaller, more affordable, we are able to increase that voltage, and that way you can test a little bit bigger transformers with the TTRU1 today compared to instruments in the past. And I would say more importantly is that the TTRU1 is capable of injecting or sourcing more excitation current. in excess of 1 amp, where a lot of the old handheld turns ratiometers, that excitation current was a lot lower. So if you did have a short or a problem in the transformer, the turns ratiometer may not work to your expectations. So with the TTRU1 having that higher voltage and higher excitation current, we can ride through some of those problems and then give you the turns ratio result that will identify where that problem exists. I hope that answered the question there.
Great. Thank you very much. I've got another question that's come up. Customer is in HVAC, and he was taught Megohm test motors to test Megohm test motors at double their operating voltage. So about 1,000 volts DC for a 480-volt motor. Is that backwards from what you've recommended?
Yes, I can definitely answer that question. That usually depends on IEEE standards for motors. Usually what we recommend, what I mentioned in the slides previously, is you always test lower than whatever is recommended. If you are doing a high pot test, then it would be something different, that you are injecting higher voltage to see if it withstands that particular voltage. But usually if it's 480 volts, you are only going maximum to 500 volts.
Okay. Got it. Thank you. That's useful. The other question we had was, what test voltage is required for testing distribution transformers?
Well, yeah, again, talking about turns ratio testing. For distribution transformers, the 8 volts that has been used in the past, it is sufficient. But as you go up to, a little bit bigger pad mounted distribution transformers, maybe 3-phase pad mount distribution transformers, you might need a little bit more. And that is why we have that 30 and 62.5 volts available in the basic and the advanced models of the TTRU1. That would certainly be the most voltage that you would need, I would say, for any small pad mount transformers. When you get into larger power transformers, then you really want to induce or inject up to 250 volts. And of course, Megger has instruments for that. But looking at the distribution side, 30 volts is plenty. 62.5 allows you to go up, maybe a little bit bigger, 5 MVA, something like that.
Okay, great. Looks like one of the questions wasn't answered for bidirectional transformers. Should the TTR testing be run in both directions?
That should not be necessary. So
Okay.
this transformer, from the description, it sounds like it can do either step up or step down. And that is actually 2 different ways of performing the tests that we have in some other products like the TTRU3, where we can inject voltage on the primary and measure on the secondary, or alternatively, we can inject on the secondary and measure on the primary. And the only difference that we see when doing that test is that the percent error is flipped around the 0% axis, if you will. So if you did step down and you were injecting 50 volts, say you got a percent error of plus 0.15, if you were to then turn around and inject voltage on the secondary to induce up to 250, you would see the percent error as minus 0.15. And that's really the only difference that you see with respect to step up versus step down. But the 2 instruments that I discussed today were both primary injection kits, where we just inject on the primary winding.
Right. Okay. Great. Thank you. Looks like the last question I have is, do I need to perform turns ratio if I'm already performing go and no-go testing?
That is a great question. And when I was visiting one of the rural groups in Pennsylvania, where the factory is located for this product, one of the comments from the class there was that they were performing the go no-go testing with a different piece of equipment. But in their experience, go no-go would show a transformer to be in proper working order. But then when they put the transformer into service and then they went to measure the voltage that was being delivered at the receptacle in the user's house, they found that it was less than the 120 volts that they expected. And that is certainly a case where performing turns ratio tests would have identified that problem, where, go, no go, it's looking for, dead shorts, it's looking for open circuits, it's looking for the transformer core there doing its job, but it's not looking at the finer details that can be found, like shorted turns, things like that, that turns ratio is really meant to do. So if you're doing one, you should definitely be doing the other. And again, with that additional information, you can make better informed decisions about that asset and the maintenance activities that you would want to undertake.
Great. Thank you very much. And thank you both, Yash and Ken. This was very informative and very interesting. I love when we get technical. Anyone else, if other questions do come up afterwards, definitely reach out to us. You can email me at the email address shown on the last slide here, and we'll be happy to get the answers for you. And or if there's anything else that we can help you with, if you have any questions, if you'd like a quote for any of these tools, help with placing an order, or anything else, definitely just reach out to us, and we're happy to help any day. So, guys, again, thank you very much for the presentation, and we look forward to meeting with you again.
Yes, thank you, John. Thank you, everyone.
Sure, you're very welcome.
Thank you,
That
John.
concludes the webinar. You're very welcome. Take care, everybody. Have a great day.